Writing the names of binary molecular compounds, what this means is that we're writing it, binary means two, and we're writing it for two nonmetals. You likely already know how to name a couple of these. So one example you might know is carbon monoxide or carbon dioxide. So the way that we name these is we start with the prefix before the first element, unless it is mono. So if there's only one of the first element, we don't put that in front of it. And we do, when we're naming these, we name the first element that's furthest left and down on the periodic table. Another way you can think of it is one that is most like a metal. They're not metals, but they're the one that's closest to the metals on the periodic table. And we use the full name of the element. So carbon is our full name. We write the second name of the element. We change the ending to IDE, just like we've done in the past, but these are not ionic compounds. They are covalent because they're made of two nonmetals. Then we put the prefix in front of each name to indicate the number of atoms. If the first one is just one, we do not use the prefix mono. So just as in our example of carbon monoxide, which is CO, there's only one carbon, so we do not include the monocarbon. We just call it carbon. We put the prefix in front of the oxide, and it becomes carbon monoxide. Carbon dioxide, we follow the same pattern when we've got two oxygen. So carbon first, then dioxide. The di tells us that there's two oxygens. The prefixes that we use for naming our molecular compounds are the same as what you would see for geometric shapes, and these are the same that we saw for our hydrated compounds. One is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. If our element begins with a vowel, we drop the last A in these prefixes. So let's look at naming a binary molecular compound. Binary because it's two elements. We've got B and F. We want to start by naming the first element. So in this case, our first element is boron. We name the second element and change the name, the ending to the name to IDE, so fluorine becomes fluoride. We add our prefixes to each. So there's only one boron, mono. There's 3 fluorides, so it's trifluoride. But we don't include the mono in the name for the first element. So this would be boron trifluoride. Here's an example for you to try. Name the following compounds. N would be nitrogen, and there's just one, so we wouldn't include the mono. 2 oxygens, so it would be nitrogen dioxide. P is phosphorus. There's 5 chlorines, so it would be phosphorus pentachloride. 2 iodines, so it's diiodine heptafluoride because of the 7 fluorines. So diiodine heptafluoride. Now let's try going from the name to the formula. So typically this is a little bit more intuitive. So we want to identify the symbols for the elements. So nitrogen is N, oxygen is O. We want to write the formula using the prefix number as the subscript. So di means 2, penta means 5. So we're going to have N2O5. Here are some examples for you. Pause the video and write the formulas. So dinitrogen tetraoxide would be N2O4. Sulfur hexafluoride is SF6. And this is a really fun gas that is more dense than air. And it's non-toxic, so you can inhale it. Because it's more dense, it makes your voice go lower. Diarsenic trisulfide is As2S3. Danger, dihydrogen monoxide contamination in water. So what does this mean? Dihydrogen monoxide. Well, dihydrogen is H2O. So it's saying water contamination in water. A few years ago, there was a panic started when an announcement was made on April Fool's Day that dihydrogen monoxide was contaminating the water. So it's really important to have a little bit of chemistry knowledge to avoid this kind of panic. We're now going to look at naming acids, but let's talk a little bit about what they are first. So acids are molecular compounds that form H+ or a proton or a hydrogen ion when dissolved into water. The way that we indicate something is dissolved in water is we put an AQ in parentheses following the formula. And the AQ stands for aqueous or aqueous, depending on how you prefer to pronounce it. Now, acids have a sour taste, and you're probably familiar with this if you've ever had citrus fruit. You know that it's got kind of that sour taste to it. They dissolve lots of metals, but they do not easily dissolve gold, silver, or platinum. These are part of the reason why these metals are precious metals, because they're very unreactive. We can dissolve gold and silver, but it takes a very special mixture of very strong acids to do that. And when we write these, we generally start the formula with H, and the number of H's tell us how many protons possibly could be dissociated or given off when dissolved in water. So there's two different ways to name these acids depending on their structure. So if they contain oxygen, they're going to have a polyatomic ion in them. If that polyatomic ion's name ends in ATE, we're going to change the ending to end in ic, and we add the word acid. So an example of this would be phosphoric acid. It is made out of phosphate, and so because it's phosphate, the ending gets changed to ic. So phosphate becomes phosphoric acid. If it ends in ITE, which is less frequent, but we would change the ending to OUS. And so an example would be sulfurous acid. SO3 is sulfite, and the name becomes sulfurous acid. Now these are oxygen containing, so oxyacids means oxygen containing. with a polyatomic ion. Binary just means two elements, so it's hydrogen and another element. So when we have just two, we add the word hydro in front and change the ending to ic. So an example of that is HCl is hydrochloric acid. The hydro because there is no oxygen. So let's name HCl. We want to identify the anion. So it's Cl. There's no oxygen here. Okay. So we're going to change the chloride to chloric. We're going to add the hydro because there's no oxygen, and it becomes hydrochloric acid. Acid gets added to the end when our formula starts with H. Okay. Another example for oxyacids. So we want to identify the anion. We've got oxygen included now. So we've got sulfate. Sulfate becomes sulfic. Okay, it should be sulfic, but history has changed it to sulfuric because it sounds a little bit better. So this is a little bit of an exception. Instead of being sulfic, sulfuric. And we write the word acid at the end. There is no hydro because this contains oxygen. So H2SO4 is sulfuric acid. Name the following. Pause the video. Name the following acids. H2S, because there's no oxygen, becomes hydrosulfuric acid. Again, because there's no oxygen, the prefix hydro gets added to the name. H3PO4 has oxygen, so there's no hydro, and this becomes phosphoric acid. It would be phosphate, so it becomes phosphoric acid. NO3 is nitrate, so it becomes nitric acid. Again, there's oxygen, so the name does not begin with hydro. How do we write the formulas for acids? We go the other direction. So if it ends with the word acid, we start the formula with H. And we think about this similar to an ionic. It's not ionic, but we think about it in a similar way. So we balance the charges. If it starts with hydro, it's just one other element. If there is no prefix, that means that it is a polyatomic ion. If it ends in ic, it's the polyatomic ion ending in the ate suffix. If it ends in ous, it's the polyatomic ion that ends with the ite suffix. So here's an example, hydrosulfuric acid. So the symbol of the cation with its charge, because it says acid, we know that the cation is H+. We want to write the symbol for the anion. So our anion is going to be sulfur. We know this because it starts with hydro, so there is no oxygen. If we look at sulfur's position on the periodic table, it's a -2. Now the charge without the sign becomes the subscript. We want to write AQ at the end to recognize that it's an acid dissolved in water. If we didn't write AQ, H2S is frequently a gas at room temperature, and so this AQ helps us to recognize that it's an acid dissolved in water. We check our total charge. So we've got 2 hydrogen with a +1 charge for a +2 total. We've got 1 sulfur with a -2, -2. So our formula is going to be H2S. How about carbonic acid? So carbonic acid, there's no hydro at the beginning, so this means that it's going to be a polyatomic ion. The ick tells us that it's going to be carbonate. The acid tells us that our cation is an H+. Our anion is carbonate. Our charge without the sign becomes the subscript. And we get H2CO3. We do need to include the aqueous to show that it's dissolved in water. We can check our total charge. We've got 2 hydrogen with a +1 charge. And our carbonate, 1 carbonate with a -2 charge. So our charges cancel. So here's a practice for you. Write the formulas for the following acids. So nitric acid. So acid begins with H+. Nitric, there's no hydro, so this is going to be containing oxygen, so it would be nitrate. We cross our charges to get our subscripts, and we write AQ. So nitric acid would be HNO3. Phosphoric acid, again, it ends in acid, so our cation is H+. There's no hydro, so that means it's going to contain oxygen, so this is phosphate, PO4, 3-. Cross our charges, and we get H3PO4. Write AQ to show that it is an acid. Hydro means that it is just one other element. So the acid tells us it's H+. The hydro says that this is just bromine. So our acid would be HBr.